Hello everyone, I'm Li Zheng. I will be presenting our learning-based approach for video denoising. Videos captured under low lighting conditions are noisy, as you can see here. The noise reduces the visual quality of the videos and negatively affects video processing tasks such as object detection, object tracking, and compression. Therefore, video denoising is an important problem. There has been a lot of research on video denoising, which I'm going to discuss by categorizing them into two classes: RGB video denoising and raw video denoising. A large number of traditional and learning-based approaches have been proposed to denoise videos by modeling the noise using additive white Gaussian noise (AWGN). However, since these approaches are specifically designed to remove AWGN from RGB videos, their performance on real-world videos, which usually have a more complex noise, is suboptimal. To address this issue, a few recent methods propose to perform denoising on raw videos by accurately modeling the noise. Specifically, Chen et al. Proposed to train a network to denoise each frame and enforce the result of consecutive frames to be similar. However, the method does not utilize the information of adjacent frames. Yue et al. Proposed to incorporate the information of neighbor frames by implicitly aligning their features. However, since they implicitly align the images, their method is not able to effectively utilize the information of neighbor frames. A couple of approaches propose to generate a denoiser image from a set of both images. While these methods are image denoising approaches, they can be used for video denoising as well. Specifically, these methods use a network to estimate a kernel, which in turn is used to combine the noisy images. However, these approaches are limited to the size of kernel and can only handle small motions. Our goal is to design a denoising system that avoids the limitations of the previous approaches. Similar to the recent methods, our system works on raw noisy videos to generate a denoised raw video. This video is then converted to an RGB video using ISP. In the rest of the talk, I will explain our approach by showing the RGB frames. However, note that our method works on raw images. To produce temporally coherent videos, we would like to utilize the information of a set of consecutive noisy frames to generate each denoiser frame. I'm going to explain our approach with 5 frames, but a larger number of frames can also be easily utilized. In contrast to the recent approaches that implicitly align the neighbor frames, we perform an explicit alignment and thus break down the denoising process into 2 stages: alignment and fusion. I'm not going to explain each stage in detail. The goal of alignment is to generate a set of aligned images by registering the neighboring frames to the center frame. So obviously, the center frame can directly go to the aligned stack. To generate each aligned frame, we first generate a flow from the neighbor frames to the center frame, and then warp the neighbor frame to the center frame. This process can be done for all the remaining images to obtain the aligned stack. Then, the aligned stack is fed to future component to generate the denoised version of the center frame. The major problem is that, for temporally distant frames, the aligned quality could deteriorate due to complex larger objects and camera motion. Inspired by Tassano et al.'s approach, we address this problem by performing the denoising in multiple stages. Specifically, we use our denoiser to generate an intermediate denoiser frame by processing 3 consecutive frames at the first stage. The intermediate denoiser frames are then used as input to the denoiser in the second stage to generate the final denoiser frame. In this way, the denoiser frame is obtained by combining the information of 5 neighbor frames, but each denoiser only processes 3 consecutive frames, thus avoiding aligning temporally distant frames. Note that if we want to utilize a larger number of frames to denoise each frame, we can simply increase the number of stages. In our system, we use convolutional neural networks to model both the alignment and the fusion stages, and the networks in all the denoisers have shared weights. Next, I'm going to talk about the training. To ensure our system produces visually pleasing results with realistic details, we train our multi-stage denoiser in an adversarial manner. Specifically, we use a discriminator to distinguish the fake results generated by our denoiser from the real ground truth images. Here, the multi-stage denoiser is the generator, and the discriminator penalizes the generator for producing implausible results. Unfortunately, by using a naive adversarial loss, high-frequency artifacts appears in the smooth regions of the generated frames. To see this, let's look at a denoiser frame generated by this approach. I'm going to focus on the insights to better show the problem. As indicated by the arrow, the result of generative adversarial network has a high-frequency artifact in the smooth regions. This is mainly because the discriminator interprets the high-frequency artifacts as real textures. To address this issue, our main idea is to provide additional information to the discriminator to be able to distinguish the smooth regions from the high-frequency areas, and therefore detect the artifacts in the smooth regions. We do this by conditioning the discriminator on the gradient mask. As shown here, the gradient mask clearly detects the high-frequency areas. To condition the discriminator on the gradient mask, we simply concatenating the gradient mask with the denoiser frame. In our system, in addition to the adversarial loss, we also use L1 and VGG losses. The details are in the paper. As shown here, conditioning the discriminator on the gradient mask removes the high-frequency artifacts in the smooth regions. Next, I discuss the process for generating our synthetic training set. We first obtain a set of high-quality 4K videos from YouTube. We then downsample each 4K video to 1080p using a Gaussian kernel. This step mitigates the noise, for example, the compression artifacts. This 1080p sRGB datasets can be synthetically converted to raw domain using a processing pipeline proposed by Brooks et al. We then add Poisson and Gaussian noise to the raw dataset. This process gives us the noisy and clean training image pairs in raw domain. Now let's look at our results and comparisons against state-of-the-art methods. Specifically, we compare our method against image denoising approaches, DIDN and KPN. We also compare against video denoising methods, VBM4D, FastDVDNet, and RVDNet. First, we analyze the performance of our approach against these approaches on our synthetic 1080p testset. We evaluate the results using PSNR and two perceptual metrics, LPIPS and SSIM. The lower LPIPS values correspond to better results, while PSNR and SSIM higher is better. As you can see, our approach produces overall high quality results and is significantly better than other approaches in terms of all metrics. Next, I'm going to show comparisons on one of these synthetic videos. This is the noise video. Our approach generates good quality results without any obvious flickering artifacts. Compared to other approaches, we produce a temporally coherent video with more details. Next, we look at the performance on real test sets. This is an outdoor video. We generate sharp results while significantly mitigating the flickering artifacts. Compared to other methods, our results are sharper and has less flickering. In conclusion, we propose a raw video denoising system for effectively denoising high-resolution videos. We achieve this in part by using a multi-stage architecture. We showed the advantage of using an explicitly trained flow-based alignment system. We achieved the high texture quality by using an adversarial loss and condition on the discriminator and the gradient mask to avoid high-frequency artifacts. Our results showed significant improvement over existing methods. This is my talk. Here are the acknowledgements. Thank you. I'd like to take any questions.